Okay. Right, ladies and gentlemen, my presentations usually run too long. I tried to make this one shorter, so I should see if I can go through it fairly quickly. The crouch speed formula, some of you may have heard of it, some may not. Right, first failure. Right. Try and fix that one. So, knowing how fast your boat goes is something that everyone wants to know. Okay. And so for new boat proposals, existing craft, if you change the power on your boat, you want to know the difference in speed. If you change the weight, you want to know the difference. So weight and power are the main factors, but hull size is actually important too. And in crude terms, the longer your boat is, the more efficient it is. That's a very crude description, but it works out in practice. We'll talk about it more later. Hooray. So the basics for this crouch formula, the assumption, this is a little bit technical, that the resistance per ton of displacement is proportional to speed. Resistance, of course, is made up of two main things. One is the wave making and one is friction of the water. And they vary differently as speed increases. So it's a bit odd that this assumption actually works, but they have, broadly this is true, they found this in tank tests, even though in theory it doesn't really work. So if you're doing calculations and haven't got access to a test tank, then Daniel Savitsky's the modern way of calculating the performance of your boat. That's quite a long-winded way of doing things. And a simple but useful formula is invented by this chap, George Crouch, you see here. Before, in the 1920s, he was a Webb Institute professor of mathematics, but also a successful boat designer. These are some of his boats, Gold Cup races, American Gold Cup races. Baby Bootlegger was quite famous, one of the really pretty ones, known as the diamond-studded cigar because of all the brass screws in its hull. And this Rainbow, which was deemed illegal and disqualified after winning one of the races, or the championships, actually had a surface propeller in the 1920s, designed by Hickman, the sea sled man. Right, there are other formulae. Keith, Hacker, Burgess, Rays, Wyman is a recent one, and they're all useful, but I'm talking about Crouch, which is one I use quite a lot. There's a UK naval architect, Barnaby, basically in his book produces a similar formula, which I'm sure came from Crouch. He uses different units, and he uses a constant K rather than a constant C. Crouch, being American, in those days used miles an hour, feet and pounds. Barnaby used knots, feet and tons. And you'll find, or I will tell you forcibly, that units are important. This is the original Crouch formula. So you can see there's very little to it. C is the Crouch constant. V is speed, W is the total craft weight, everything. P is the power. We'll go into those a bit later on. You can use any units you want. I'm not going to give you numbers for this. This is something you've got to work out for yourself, for your own boats. But the units are free, but you've got to be consistent and use the same ones all the time. C's a constant, it's not a dimensionless coefficient. So it's fairly crude formula. The main thing is that you can make it work. You'll see here, I've taken these from Barnaby's book, but Crouch's C and Barnaby's K are very similar in this respect. And I'll come back to this later. You'll notice that the actual constant increases with the length of the boat. And that's important. It's something that people forget about. So it's useful for comparing, the original formula is useful for comparing like-sized boats, same length and of same or similar type. And the thing you need to do if you're interested in this or you manufacture boats is to log known factors from all your own boats. Keep a table, make yourself graphs, or put them into a spreadsheet, and use consistent units, as I keep saying, and I'll keep saying that. You must input the correct parameters, and the actual number, of course, that comes out at the end depends on the units you use. But as long as you use the same units all the time, then your numbers will be consistent. So with the power part of it, I prefer to use shaft horsepower. You can use installed brake horsepower. You could use equivalent kilowatts. As long as you use it all the time, you're okay. Don't mix them. But and don't mix brake horsepower and metric horsepower, because there's a subtle difference there. But bear in mind that quoted outboard power is usually shaft horsepower. It's measured down at the prop. So if you're comparing outboard boats and inboard boats, then what I do is take the inboard ones and put in a... hope you can I move that up a bit? Down. No. The bottom bit doesn't matter too much, but basically you need to put in a reduction for the transmission losses. So if you're given an installed brake horsepower of kilowatts for your inboard diesels, you've got to knock something off for the transmission. The jet manufacturers usually knock off 3% for the jets. Just about see it at the bottom. I usually knock off 5% for surface drives, and you can do about sort of 6 to 8% for stern drives, depending on the... Talk to the manufacturers and they'll tell you, but you need to knock something off to get shaft horsepower for your inboards. So that if you're comparing one of your boats with inboard power against one with outboard power, you're actually using the same power. Speed. Let me just go back. Excuse me a sec. I'm losing the bottom of all these slides. But you can use whatever speed you want. Speed units, knots, miles an hour, kilometers. Just be consistent. That's the main thing with speed. And with weight, use whichever units you want and be consistent again. But remember that the weight is the actual displacement, the weight of the boat on the water. It may seem quite obvious, but people do forget it. So it includes the whole lot, you know, all your weight, clothing, fuel, water, equipment, food, booze, everything applies to the dent the boat makes in the water. So it's the all-up weight that you have to use in the formula, and make sure that you know how much fuel's in it and whether there's any water in the water tanks and things like that. You've got to compare craft of similar types. Obviously with these two pictures, the one's a shaft-driven hull with a lot of top hamper, and the other one is a surface-driven hull with steps. They're not comparable. You need to keep them in compartments of comparable boats. The formula is quite simple, and it won't jump this kind of gap. So you need to have separate tables. separate spreadsheets, if you like, for these. It's only based on speed, weight, and power, and so even with the same hull, it will depend. It will vary. The constant will vary depending on the drive system that you use. And even with outboards, you can mount outboards at different heights. You can have them well and truly dunked in the water so that you get good performance through hump and to get weights on plane. If you want to go higher speeds, you raise the motor up so that there's much less of the drive leg in the water and the propeller's working in semi-surface mode. This will make a difference, of course, to the overall boat efficiency, and therefore it makes a difference to your constant. So again, you have to supply, compare like with like. That's got a bit skew with, but what it basically says is that going back to where I mentioned that this constant increases with the speed, with the length, sorry, the constant increases with the length of the boat. Many people make the mistake of using a constant they've got for one boat, using it for a different length boat. They often find that the longer boat seems to be more efficient. It is in its way, although going into the mathematics behind it is more than we're going to get into our 15 minutes. And I have to do it on paper anyway. So, but we can modify this formula for length. So if your boats are all the same length, then the previous formula, or the existing one, the original one, is all you need. But if your boats change in length, then we do this modification. What you take the original, this, I'm not allowed to use the pointer, but where it says CC, that first part of the formula is the original Crouch formula. You multiply it by, well, you divide it, in fact, by the hull length parameter to the power of a quarter. Or simply you work out your original Crouch formula, and then, as at the bottom, you divide it by this hull length to the power of a quarter. That should adjust the formula for differing hull lengths within reason. None of this is super accurate. It's no substitute for doing the design job properly. This is for quick comparisons. And once you've got your table and spreadsheet worked out, and you get a feel for the numbers, you can do this fairly quickly. That's what I use for hull length. It's the working length of the hull to the heel of from the heel of the transom to the bow. I use the forward side of the tube for ribs, because if you extend, if you haven't got a tube around your boat, it's a hard hull boat, if you extend that stem line up, it usually comes to approximately the same place. So that's the way from the proper bow, extreme bow, to the heel is what I use, and I think that's probably the best, most consistent way of getting a hull length. The modification comes from basically the speed-length ratio, the Froude relationship, which does work for planing craft, although it's based on wavelength. This Froude number is speed divided by the square root of the gravitational acceleration times the low waterline, or the waterline length. You don't need G most of the time, so the simple version is the speed-length ratio that most or many people know, which is V divided by the square root of the waterline length. This is what we need for corresponding thing. I wonder where we're up to. So for equivalent speed and different length craft, this should stay constant. Now many people know that. So for a 20-foot boat, if the speed-length ratio is 6, then it's doing 26.8 knots, and for a 40-foot boat, it'll be doing 37.9 knots for that same speed-length ratio. Then the hull will look the same and act the same, and the same proportion of the hull will be wetted. So C only works for same length hulls, so if you use different length hulls, use CC all the time and collect all your proper information. Put all the information from the boats you know that you trust into a spreadsheet. Even if the craft are different sizes and you use the CC version, they must be of the same type. One of these is 51 feet, one is 45, but they're the same type. They're both stepped hulls, they've both got surface drives. So they are strictly comparable. And like for like on appendages, you know, the submerged shafts there on Miss England 2 are not comparable with surface drives. Aerodynamics, you need, if something's got tall superstructure and compared with a short superstructure, it's, there's going to be a difference. There's more aerodynamic drag on the tall superstructure. It might change the trim of the boat a bit to your advantage. You might tip the bow up a little more and increase trim, so you may not find quite so much difference, but aerodynamics makes a difference. When you're talking really fast boats with a lot of aerodynamic lift, then this constant will start to climb because more and more the boat is being held on the air and less of the hull is doing support on the water. So you have to get used to that, and right up at the top end of these really fast racing boats, this constant will start to climb rapidly. Centre of gravity position is important, craft weight is important. They are comparable, but the constants will vary a little bit. Propellers, they need to be consistent. You need a submerged propeller compared with a fully cupped surfacing propeller. There's going to be a difference. The surface prop will give you a higher constant, and the condition of the propellers count as well. Although that previous one, we did 71 knots with the intact propeller and 67 knots with the beaten up one, so it was an interesting exercise. So, cracked formula in standard form, good for same length boats, modified form, CC, for differing lengths. It is very quick once you've got everything together. So use it for preliminary estimates or talking to the customer across the table. It's no substitute for proper calculations. Do them properly. Get your naval architect to do them properly when you're designing the boat, but it can be extremely useful. I rushed it. I've got some time for questions if anyone has any. Or they can talk to me later, and I'm quite happy if people give me their email. I can always send this presentation to them if it's any help. Thank you very much.